way? Okay. So good morning, everybody. First, I kindly ask you maybe to come closer, so you will not be so dispersed around the room. It is a great pleasure for me to start the tutorials session. We have 55 registrants, much more than the attendees in practice, so I guess that some will flow during your talk and later. It is a great pleasure for me to welcome and introduce Professor Peter Voorhees from the Department of Material Science and Engineering at Northwestern University. Peter is one of the leaders worldwide in the area of physical metallurgy and related things like phase transformations and so on. And his talk will be phase field methods, fundamentals, and applications.
Could you turn down the lights maybe just a little? Okay.
We probably won't be able to see some of the slides.
Probably, yeah.
Yeah,
That's fine. Yeah, that's good. Okay, so with apologies to the experts in the audience, this is intended for kind of graduate student level material. So I first want to introduce this idea of what phase field equations are, and doing this in the very simplest contexts of two very famous ones, the Cahn-Hilliard and Allen-Cahn equations. And then what I want to do is I can't cover everything, and so what I want to do after that is kind of, with that as a basis, show you where the bodies are buried in the phase field community. And by that I mean I want to show you, give you the information you need to understand when you look at a phase field paper, what questions to ask as to whether or not the calculations are correct and whether or not the person's done a good job in ensuring that the answers that they get are real. And that turns out to be a major issue in the phase field community that isn't well appreciated. So there are a number of reviews in the literature. These are two famous ones. This one is focused primarily on solidification, as the title implies. This one is focused primarily on the physical metallurgy. These phase field methods grew up almost independently in these two communities, and the way these communities look at these models are therefore a little bit different, so that's interesting. There's a textbook now by Provatis and Elder that we have used at Northwestern in our computational materials class, and Alex Amantsev also has a more theoretical physics-oriented take on phase field theory in that textbook there. And so, as I said, I want to give you an introduction to the bargain basement, simplest phase field models you can think of, and how do you build up some, and then talk a little bit more about the challenges and limitations, and basically how you know that you're getting the right answers. And so the idea here is to develop efficient computational methods to allow you to track the evolution of interfaces. And so what you'd like to be able to do is to predict the nano and microstructure of materials, what the shapes of the interfaces are, what the compositions are, the non-uniformity or uniformity of the compositions. And this can be from anything. This can be in thin films, it can be in ferroelectrics, it can be in magnetic materials. The nice thing about phase field methods is that they're extraordinarily easy to add new physics to the equations, that therefore model other situations. And the goal here is, of course, to use these models as one stage of a materials design effort. And so to try to fix ideas, let me show you the challenges that we faced before phase field methods were around. And this is a picture of a dendrite that's growing into a liquid. And if you wanted to describe the evolution of this dendrite, in other words, predict what the local normal velocity is at that point, what you need to do is to solve a diffusion equation, classical diffusion, alpha is the thermal diffusivity, in both the solid and the liquid, which is not so bad. I mean, if you look up numerical recipes, for example, they'll have methods to solve diffusion equations. That's pretty simple. The problem with these interfaces or these phase transformation problems is that you have boundary conditions on the interfaces. And in this case, the temperature at a point on the interface depends upon the melting point. minus a capillary length, which was related to the interfacial energy, times the mean curvature. And why is this such a challenging problem? Well, if you think about setting up this problem, if you pull out numerical recipes, they'll show you how to solve this equation, and they'll say, where are you going to put the boundary conditions? Oh, okay, if I have a bar, I'll put a boundary condition at 0, I'll put a boundary condition at L, and I can solve that problem. Okay? You think about how you do it in this problem. Well, here is the interface, but this interface is evolving with time, right? So the boundary conditions, where you put the boundary conditions for the solution of the diffusion equation, change with time. And the question is, well, how do you determine the location of that interface? And you determine the location of that interface by saying that the velocity at that point times the latent heat, in other words, the heat released as the interface moves, is going to be related to the temperature gradients in both the solid and the liquid. And so this just tells you the velocity, it doesn't tell you the location. And so therefore what you have is this coupled problem where you need a boundary condition, you need a place to put the boundary condition, but you don't know where to put the boundary condition because you have to solve this equation, but that's dependent on the gradients and the temperature, which comes from this equation, but you can't solve this one because you don't know where to put this one. Okay? And these are called free boundary problems as a result. And in this case, they're highly nonlinear because the curvature here is a nonlinear function of the shape. And so what people tried to do before phase field methods is that they would take a dendrite like this and they would try to mesh this up, try to actually put a mesh on the surface of the dendrite, and then move the mesh points around according to this kind of a law, which I have a mesh point and I move it a certain distance in a certain time, and then I solve this equation again. And that basically is pretty hopeless. It basically limited these problems to one dimension. So the problem, of course, in a dendrite is that the curvature varies with position. And this is high mean curvature, low mean curvature. And so it's even more complicated in the sense that now you have to apply boundary conditions that vary with space along the interface. So not only you don't know the location, but the actual value of the boundary condition depends strongly on the shape, which you also don't know. So that's a very difficult problem. Let me give you an example for something that's more relevant, let's say to polymers or other materials where you have bicontinuous-like structures. And so this looks like a sponge, and what it really is a solution to a phase transformation problem where you have diffusion in both the inside and outside phase. The outside phase is hollow here so you can see into it. So you have, again, diffusion. In this case, it's chemical diffusion, and this is a concentration. The concentration at the interface goes like the mean curvature. This is just as we saw before with the temperature. This is the composition at a flat interface given by the phase diagram. Again, that's the interfacial energy. And the mass balance at the interface, it says the jump in the concentration times the velocity is going to be balanced by the flux flowing away, and that's the gradients in composition. And again, imagine you have this problem to solve, and you have to mesh up these complicated interfaces. Virtually impossible to do. This is what one of these interfaces look like in higher magnification. I can find my cursor. There we go. And so this is just a small section of that big picture, right? So how do you actually mesh something like this up? It's pretty much impossible to do. So this is the interface between the two phases. And so what phase field methods has allowed us to do is to compute the evolution of structures that look like this. And that's why it's become such a powerful numerical technique. And the phase field method goes back all the way to van der Waals, back in the 1800s. Cahn and Hilliard are another famous names associated with this, Landau and Ginsburg in the superconductivity field. And the idea here is very simple. You have two phases, and you have an order parameter or composition, depends upon how you want to view it. I'll call them order parameters. You could also view them as compositions as a function of x. And you have a diffuse interface, or a smooth change in composition, or an order parameter as you go through the interface. And the nice thing about this, if you think about this a bit, is that now, if you can write equations for the evolution of this order parameter, you don't have to track the location of this interface. In other words, you have an equation that holds at all positions in space. You don't have to worry about where the interface is actually located. And so it avoids the explicit tracking of the interface. You can follow these topologically complex structures, which I'll show you, and topological transitions that follow naturally. And what do I mean by topological transitions? This is a simple 2D phase field calculation of two particles sitting next to each other. And as time goes on, you can see what happens at this point. The two particles coalesce. And this is a topological transition because you go from spheres, two bodies, to a single body. If you're doing this using a sharp interface method, what you'd have to do is you'd have to do something with the mesh here that describes each one of these shapes when these contact. Phase field models, it just does it naturally. So it can follow these topological transitions. And that's why you can do things that are such complicated in their morphology and topology. And so here's my take on the very simple phase field models. And I'm going to derive two of them for you because they form the basis of every phase field model that is in existence today. And the idea is that you have a double well free energy. So this is a free energy density, two phases, alpha and beta, and there's a barrier height between these two. And you have two phases in the system, alpha and beta, and you wanted to compute the total free energy of this system, here F, and you can do that by integrating this free energy density over this box. And every time you're in alpha, you go over to here and you pick out the free energy of alpha, which is in this case 0, the way I put it together. You go over to here to beta, and every time you're in beta, you pick out that free energy. You integrate the whole thing up, and I think it's pretty clear that the integral of that whole system is going to be 0. So the free energy of the system is 0. But nevertheless, that's the way you do it. You basically go to a particular spot in the system, determine what the value of the order parameter is at that spot, put that into the free energy, calculate the free energy, and then integrate it up. And so that's the way you would do a non-uniform system with a free energy density. And so let's say you wanted to describe the interface between the alpha and the beta phases. Okay? So you want to describe the interface between the alpha and the beta phases. And so how would you do that? And you wanted to minimize the energy of this system. You wanted to minimize F. And you wanted to describe an interface between the two phases. And so the way you would do that is pretty simple, right? So in the beta phase, the composition or the order parameter would be uniform. So you sit in that well. And then when you go to the alpha phase, you skip over the interface, you're in the alpha phase now, you'd have composition that's uniform up to the interface, and you sit there. The energy of this system is still 0, right? Because you're every place in the beta phase, every place in the alpha phase, and you have this discontinuous jump at the interface. This is what I was calling the sharp interface method. This is what all of the boundary conditions that I showed you before with temperatures, compositions, etc., assume that you have this composition in the beta phase that sits here, composition in the alpha phase that sits here at an alpha-beta interface. If you use this description, again, you have to follow the evolution of the interface, which is difficult. One of the problems here, or one of the things that becomes clear, is that the free energy not only is a function of the composition, like here, but it's also a function of gradients in the composition. And what I mean by that is that, let's say I go to a particular point in the crystal, I put my finger at that point in the crystal, I determine what the order parameter is, and from that I can get the bulk free energy, the free energy density. What I'm saying here is that that's not enough in order to get the energy of the system. In order to get the energy of the system, I also have to know the gradient in composition. And this is kind of a strange idea, because what I'm saying is that if I put my finger at this point in the crystal, I don't know the free energy until you tell me what the gradient in the composition or order parameter is at that point. And physically, so let me tell you physically why this might be the case. So imagine you had atoms at this point, and there's a certain range of interaction on those atoms, certain interaction distance. And so this atom here, when the system is uniform, if you average the composition in this distance, around this interaction distance, it's the same as at this point. But if you have a gradient, this yellow one, you do that same average, you get a different value than if you had in the uniform system. It actually sits about up here. And so because of the finite interaction range of the atoms, the system knows that the gradient in the energy here will affect, the gradient in the composition will affect the energy of the system. And since, therefore, the energy of the system depends upon gradients. And that argument tells you something very important already. It says that these gradient effects scale with the interaction distance of atoms, so they're very small scale effects, right? And if you had only nearest neighbor interactions, you wouldn't have a gradient energy coefficient, but if you have second nearest neighbor, third nearest neighbors, you do. And so if you add gradients to the system, the free energy now depends upon the gradients. And this idea here, which goes back to van der Waals actually, has an important influence on what goes on at the interface. And so if you go back now to what we had before, you have beta, alpha. This is the free energy of the system now. Now you ask the question, let's minimize F with this new term. And now you have a problem, right? So you have beta that goes up to here, the order parameter for beta goes up to here, the order parameter alpha goes up to here, and what happens at the interface here to this term? Students? Infinite, right. Right. So the gradient of a Heaviside step function is a delta function. So you have problems. And so what the system says is, oh, okay, well, I have to minimize this term. What am I going to do? Well, the first thing that you could do is say, oh, okay, I know how to minimize this term. You just have no gradients, right? But you can't do that because you have to have beta on one side and alpha on the other. So you aren't allowed to have zero gradients in the system. And so you reach a compromise, and that compromise is that you have a diffuse interface. And back here, where the gradients are zero, the bulk energy wins, out here. And as you get close to the interface, in this interaction distance, this atomic scale interaction distance, the gradients begin to become important. And what that does is that the free energy, the bulk free energy of the material as you go from here to here, actually goes up, over this barrier, and back down to here. Okay? And so it traverses this unstable region of the phase diagram that in between the two spinodals, which are here and here. And so as you go from one to another, you go up and over, and that W becomes important, and that's why I put it here, because this W basically is related to the properties of the interface as it goes through here. So the properties of the interface are going to be related to the epsilon, which is this related to the interaction distances, and it's going to be related to W, which is the height of the barrier between these two, because you actually sample that barrier as you go from one phase to another. And so the actual minimum in this energy here is a little different than what you normally would see in a standard calculus problem. So what we're looking at in the normal calculus problem, I give you a function, and I say find the minimum or maximum. And that's a classic calculus problem where you just take the first derivative and set it to zero. Here what we're interested in is not the value of the function or the location of the minimum or maximum. We're interested in the function itself. In other words, this composition is a function of distance, or the order parameter is a function of distance, that minimizes f. And so we're interested in the function and not the value of the function. And so what you have to do, in order to figure out what the minimum is that you have to take a functional derivative of this equation and not a regular derivative. It's a variational derivative, functional derivative, depends upon the community that you've come from. And let me show you how this works. And I apologize for the experts in the audience. So if you have a free energy that looks like this is one dimension, this is phi dx. So we're assuming a one-dimensional profile through the interface. And you take a variational derivative, and my apologies for the mathematicians in the audience, this is not rigorous, but it gets you the right answer quickly. So if you take the variational derivative, I'll denote this by delta. And so you take the variational derivative of this integral, you pull delta through, and it operates on this term here, and it operates on the derivative. And so the functional derivative, the variational derivative of f, is just the partial of f with respect to phi times the variation of phi. It operates kind of like a differential operator in this kind of approach, which is why mathematicians don't like it. And then you have to do something with this derivative term over here. And again, it operates like a differential operator, so you get 2 d phi dx times the variation of the stuff in the inside. Variation of d phi dx like that. And so that's what we had before. So you have to figure out what to do with this. So how do you take the variation of the derivative? Well, what you do is you just interchange delta and d. So you write it as d by dx, and you move the delta on the inside like this. And now what you can do is you can just integrate by parts. And so you take the derivative and you throw it over to here, which is what you do basically when you integrate by parts. Throw the derivative over to here, and you get some terms associated with the boundaries if you integrate by parts. And now, since you've thrown the derivative over to here, you get a second derivative times the variation in phi. If you say that the value of the function of the derivative is 0 at the boundaries, in other words, we don't have any free surfaces of plus or minus infinity, you get the variation of the, you can pull this term together with this, and you get this brackets times delta phi equals phi. This method that I showed you here will always work. It will always give you the right answer. It doesn't matter whether it's a tensor or a vector. You always get the right answer if you work through this. Okay, so this thing here is the variational derivative of that functional. It involves the derivative of f with respect to phi, the gradients in the free energy, and the composition gradient, the Laplacian of the composition field. Okay, and so now you say, well, I have to set this first variation to 0. We want to extremize it. We want it at a minimum or a maximum. And so you have to set this to 0. And now you're faced with how do you set this integral to 0? There are two ways of setting this integral to 0. One of them is to choose the variation in phi in just the right way so that that integral is 0. And you can certainly do that, but that depends upon a very specific choice of the composition as a function of position. And if you want an answer that's general, you just set the stuff in the brackets to 0, and you get this. And this is what's called the variational derivative or functional derivative. These are also called Euler-Lagrange equations in the mathematics community. And so the first variational derivative of f with respect to phi is just this. And so now we have this thing here equal to 0, which tells you something about the composition profile through the interface. If you have a double-walled free energy function that looks like this, it turns out you can get closed-form solutions to this equation. And so if you set it equal to 0, you plug in the value of phi, f as a function of phi, and you have this ordinary differential equation for phi as a function of x. You can integrate it, and lo and behold, you get a hyperbolic tangent solution. And this underlies all phase field methods. And so now we have a diffuse interface that goes between the alpha and the beta phase. It's a hyperbolic tangent. And the length scale for the width of the interface, as it will become incredibly important, is given by the square root of the height of the barrier times the interfacial energy times the gradient energy coefficient. Kind of as I hinted at the beginning is what would happen. If you have a system with a conserved order parameter, you have to put in conservation, and you do that with the Lagrange multiplier. Repeat the process, and now you get the result that the functional derivative df d phi is equal to lambda, which is basically, now it's sometimes called the generalized chemical potential, is equal to the stuff on the right-hand side. So if you wanted to describe diffusion, you say that the flux is going to be given by m times the gradient in the chemical potential, or m, there should be a gradient there, times the derivative of the variational derivative. You'll see that written in the literature a lot. And so that's an expression for the flux. And so this first term here looks like a classic diffusion equation, and the second term here is the correction due to interfacial energy. The concentration is conserved. You put this into here. And so this is a conserved quantity. I'll be using conserved and non-conserved order parameters a fair bit as we go. So this is a conserved case. So it says that the flux is conserved. You put this into here, and this is what's called the Cahn-Hilliard equation. And this is one of the two basic equations that make up all phase field models, is the Cahn-Hilliard equation. It's basically the Laplacian of the variational derivative of f with respect to phi. And the key thing here is that there's a Laplacian, and the Laplacian comes from one of the gradients comes from conservation, the other one comes from the gradient of the chemical potential, and that's what gives you the Laplacian in front. And so whenever you see a phase field equation written, you can tell whether it's conserved or not just by looking at whether or not there's a Laplacian that sits in front of one of the brackets here. And so this Cahn-Hilliard equation was motivated by there's Cahn-Hilliard study of spinodal decomposition. And the idea here is you quench a material from high temperature to low temperature, it phase separates, and the phase separation process is described by this equation. This equation, if you wrote a finite difference solution to this equation, you basically finite difference in times, forward Euler, spatial finite differences. This equation requires about 25 lines of MATLAB code. Everyone in my phase transformations class, my kinetics class for graduate students, they all write an equation, a program to solve this equation. It's extremely easy these days to do. And I'm going to show you some results that we've done with large-scale systems with 1024 cubed grids. These are very, very large calculations. But I wanted to show you what happens if you start off with a volume fraction of about 50%. The system undergoes coarsening. And this is only a small section of this data. And this would be completely impossible if we did it any other way than a phase field method. There's another equation that's important, that one of the two that make up a typical phase field model. And the other one is called an Allen-Cahn equation. And it's exactly the same as the Cahn-Hilliard equation, except for one important difference. And that one important difference is that it's non-conserved. And this is motivated by Allen and Kahn's work on order-disorder transformations. It also comes from Ginzburg-Landau theory in the superconductivity area. And so this is a picture of an order-disorder transformation where you have atoms that live on sublattices and their antiphase domain boundaries. So these could easily be spins, magnetic spins. You see this all the time in the magnetic materials literature, these kind of Allen-Cahn equations. Exactly the same free energy function. You go through exactly the same variational derivative to determine the equilibrium state of the system, but since it's non-conserved, instead of a Laplacian sitting after m, there's nothing. And basically what this says is that the order parameter just moves depending upon gradients in the bulk free energy. So there's no long-range diffusion. So it's just gradients in the bulk free energy. So let me give you an idea of how this works. So here's f as a function of phi. I start the system off here. Let's see if this works. Okay, I start the system off here. The gradient in f with respect to phi is positive. There's a minus sign here, and that says that the time rate of change of phi with respect to time is negative. And so the order parameter moves down in this direction. And so this model is essentially what happens if you put a marble on top of this free energy surface. Put a marble here, and it will roll down to the bottoms of the wells. And it can roll down to the bottoms of the wells because it's non-conserved. It just kind of can move. It doesn't have to worry about what all the rest of the stuff is doing in the structure, because locally I can just flip the spins or I can just flip the compositions, and it doesn't matter. It doesn't change the free energy of any place else in the system, unlike the case when it's conserved. And so those are the two basic phase field equations, Allen-Cahn and Cahn-Hilliard. And if you do the simulations, you get slightly different structures. This is Allen-Cahn. This is Cahn-Hilliard. You can see that they look a little bit different. What we did here is we chose a 50-50 mixture of the two phases. And so what that meant is that we were sitting right here, and the system doesn't know whether to roll in that direction or that direction. And if your numerics are very good, it will sit there. And you get very different structures. And so this is the Gaussian curvature as a function of position, and this is really quite a different structure. And so now you go back to the problem that we're interested in. So you have this dendrite that's growing into the liquid. You have diffusion, interfacial energy, that the temperature goes like interfacial energy times the mean curvature. Latent heat released at the interface that's diffused away by temperature gradients. And you want a description of this in a phase field model. And it looks like this. And you just take the conserved equation for the heat and a non-conserved equation for the interfacial energy. And let me show you how these two things work. So this looks like the classical diffusion equation, right? And so what you do is you add a source term to the diffusion equation that's related to the time rate of change of the order parameter. P is some polynomial. And so how does this equation work? So this is phi is a function of x. And when you're over here, and let's say the interface is moving in this direction. You're sitting over here. What's phi as a function of t, d phi dt over here? It's near 0, right? You're far away from the interface. If it's 0 over here, this term isn't present, and you get good old diffusion. When you get close to the interface, let's say you're sitting right here, your observer sitting, the interface is moving past, it's pretty clear that phi begins to change. As phi begins to change, this term turns on, and that gives you latent heat. And so this equation here gives you diffusion when you're far away, and it gives you this condition when you're up close to the interface. So it captures the release of latent heat, and it captures this. And so where do you get this term here? That comes from here. Here's epsilon, right? Whenever you see epsilon, you think of interfacial energy. So here's the interfacial energy, and here's the order parameter term. And again, this is a polynomial in the order parameter, and it depends upon the temperature. And so these two things are coupled. This model goes back to some work at Fix. Actually, Langer, in '86, wrote these equations down. And when I was a postdoc, I went to the Institute for Theoretical Physics, and Jim Langer came up to me and said, I have these notes on this model for solidification. Would you be interested in looking at them? I said, nah, I'm doing other stuff. What a mistake. And actually, the cool thing in his notes, actually, at the very bottom, on the last page of his notes, he said, this model is too nonlinear and complicated to ever be of any use. And of course, he told me this when I was a postdoc, and I said, well, geez, okay. I don't know if I want to push on something that's of no use. So anyway, and what's happened is that computers have become more powerful, and as a result, these things are very actually useful. And so the idea here, so let's go back to here, okay? So the idea is I give you the interfacial energy, I give you the diffusion coefficient, I give you the latent heat and thermal conductivity, and then I go into this phase field model and I pick epsilon. We kind of already know how to do that. We know how it's connected to the interfacial energy. Tau, and the polynomial such that a solution to these equations is related to a solution of those equations. Okay, and let me show you the implications here. Here's the implication. So this is a René Magritte. He's a Belgian surrealist painter. This actually sits at the Art Institute of Chicago. So for all those who haven't visited Chicago, you should visit the Art Institute of Chicago. This is actually recently, I'm going to plug for Chicago. It was actually ranked the #1 museum in the world by TripAdvisor just a little while ago. And for those of you who don't read French, it says, this is not a pipe. And so the question here is, what does this have to do with phase field models? And the problem with phase field models is that you can get things that look just like a pipe, but in reality, they're nothing like a pipe. And I want to show you what I mean by that. And so there are two schools of thought. And this basically is reflected in the way these phase field models grew up. One in the solidification literature, one in the physical metallurgy community. One of them is it's a computational engine, and I kind of showed you that that's the case in the solidification community. The other is that it's somehow related to a first principles method, and this comes from the physics and physical metallurgy community. And I want to talk about these two schools of thought and to give you some perspective here as to what the problems are. And this is my entree into where the bodies are buried in the phase field method. So I showed you that if you have a free energy function that looks like this, you have a diffuse interface, you have a characteristic length scale that I showed you before with that hyperbolic tangent function that looks like epsilon related to epsilon and w. You have an interfacial energy that's the product of epsilon and the square root of w. This is classic Cahn-Hilliard van der Waals theory of fluids. The problem here, if you consider this to be a first principles method, is that if you walked down the hall to your friendly statistical physicist and you showed him or her this free energy function, and you said, well, I want to calculate W from first principles. I want to calculate W. And what she would tell you is that, no, the free energy function doesn't look like this. It looks like that. And the problem is that this free energy, this part of the free energy function is in the unstable region of the system. In other words, if I put a little bit of material of composition here in between these two spinodals, it will spinodally decompose. And that's what I showed you, those pictures, right? Those pictures I just showed you, I quenched to 50%, and I end up with this beautiful spinodal structure. And what that means is that it's impossible to measure the free energy. Because as soon as you put a system, let's say you're doing a molecular dynamic system, as soon as you put that system together and you allow the atoms to begin to move, and you wanted to measure the thermodynamic fluctuations and the entropy, which you need to do to get a free energy, it would phase separate. It would change into, it would spinodally decompose. Whoops. And so the answer really is that is what the free energy looks like. And in fact, it's even hard from a statistical mechanics sense to go from here even into this metastable regime and get closer and closer to these spinodals. Because as you get closer and closer to these spinodals, what are you doing? You're approaching a system that's becoming more and more unstable. So the problem here is that you need to know F in the unstable region. The interfacial energy depends upon W. So it's difficult or impossible to get these free energy functions for first principles. The closest thing that people have done that I'm aware of is this very nice work by Alphonse Fenel and Jan Lebois. And what they did is they started in the bulk, and then coarse-grained in a very clever way to get really very close here, and try to patch in this unstable free energy function based upon this idea of basically scaling the fluctuations in a certain way. But it's a very difficult problem, and it's the only problem that I've done before. And so you look at this and you say, well, okay, well, we have a problem here, right? I can't get W. Well, okay, do I kind of pack up my bags and go home, or what do I do? Well, the answer that people said, okay, wait a minute. I know the diffusion coefficient, the interfacial energy, and the thickness of the interface. And if I give you these three parameters, I can go back into the phase field method. Let's just pick two now. So interface energy and thickness. If I give you the thickness and the interfacial energy, experimentally measured quantities, so you go to David Simon's lab and you measure the thickness of the interface, or you do a molecular dynamics calculation of an interface and you measure the breadth of the interface, which you can do. That's a well-posed problem. So I get this and I get this. I have two equations and two unknowns, and I get epsilon and the W that I can't calculate from first principles, and you say, okay, I can do a calculation, I'm happy. And then you go and you find out, well, what's the real problem here? Okay. So I'm going to therefore have an interface thickness, and to do a calculation, I have to resolve this diffuse interface. And what that means is that I have to place mesh points in my calculation in this diffuse interface. I have to put at least 6 to 10 mesh points in that diffuse interface in order to resolve it, okay? And so let's see the implications of that. So how thick is an interface? Pick a number, a nanometer, okay? I think it's a nanometer. This is a 100 micron scale bar. So you take a ratio of 100 microns to 1 nanometer, that's 10 to the 5th. I have to put 10 mesh points within that interface width, so that means 10 to the 6th. So to do a box, 3D box of this, by this, by this, that's 10 to the 6th cubed. If I want to do this, let's say that's 10 by 10, I need a grid on the order of 10 to the 7th cubed. So Langer may have been right. You can't use this method to do anything real with it. If you're doing nanoscale structures, it gets a little bit easier, right? You cut this down by a factor of 100, let's say. You might be able to get away with it using a real interface thickness, but in general you can't. And that's really the problem with phase field models. And that's really the problem with phase field models. In fact, some people have said that if we had started with phase field models, we would have been delighted to figure out how to do sharp interface calculations. Okay, so here are the equations I gave you before, and we're in this conundrum that we have this problem of how do you pick these parameters to reproduce the real problem. And we know that it's hopeless to pick a real interface thickness. And so what you might want to try to do is to say that, well, what I'm going to do is I'm going to pick the parameters such that the thickness of the interface times the curvature is much, much less than 1. What do I mean by that? So in other words, rather than scaling your mesh on the real interface thickness, I'm going to scale the mesh spacing based upon the radius of curvature of the object here, which would be a big deal, right? Because now, if the radius of curvature here is 10 microns, my scale of my mesh is on the order of microns now, and not on the order of nanometers. And that's what most people do, to make it computationally tractable. And so the idea here is to look at this limit of the equations when the thickness of the interface times the mean curvature is much, much less than 1, hopefully about 0.1 or so. And you want to look, so this is now a parameter in a matched asymptotic expansion of the phase field equations that you have to worry about in terms when you do the phase field model. And if you do the matched asymptotics correctly, that's interesting. I didn't turn Skype off. Hopefully she'll give up. Okay, wait a minute. That's really amazing. Okay. That's what happens when you have. Oh, there we go. Okay. Okay, and so if you do that, you can basically calculate what goes on up here, and this is people have done better than this now, but not too much better. And so this is a 3D calculation of the very tip of a dendrite, using this idea where you write the equations out where the thickness of the interface times the mean curvature is much, much less than 1. Oh, jeez. Sorry. Okay. And so there are two ways of doing this matched asymptotic expansions. One of them is to say, well, I want to let this interface thickness be very small. And you can do that by letting epsilon go to 0. And if you let epsilon go to 0, if you want this to be finite, you'll let w go to infinity at the same time. And so when you look at the literature, you'll find two kind of asymptotic expansions. One associated with letting the width of the interface going to 0, which turns out to be not that computationally helpful, but it still enables you to connect these equations to the sharp interface equations. The other one is more useful computationally, is where you just say that the interface thickness is small on the scale of the mean curvature. 1 over the mean curvature. Okay, so let's go back to this equation. So here we have a model of a interdiffusion. So you have now a dendrite or any body, let's say the spindle decomposition process, where you have a liquid and a solid. The diffusion coefficient in the liquid is 10 to the 5th higher than the diffusion coefficient in the solid. So you go from liquid to solid, you have a big jump in the diffusion coefficient, that's kind of well known. You solve diffusion equations in the liquid and the solid. I'm sorry, you have a mass balance at the interface that says the velocity times the amount of material rejected at the interface is diffused away by concentration gradients. You have the concentration goes like what you have at a flat interface times the interfacial energy times the mean curvature, and you have diffusion equations. And so again, this is a dendrite, but it's growing by solute. If you're doing a precipitate growing into a supersaturated solution, this would be the model you would use. Evolution in films, it's the same sort of deal. And the key thing I want to point out is that you have this enormous change in the diffusion coefficient. And so what do? So you have the diffusion coefficient that goes from dl to ds across the interface, right? And so the thing that you're tempted to do, therefore, is to say, well, we'll just let the diffusion coefficient vary with the order parameter through the interface like this. And you'll see this all the time in phase field methods as well. So you start off, you're at 0 and 1, and what you're going to do is you're going to take the free energy of the system now is a linear combination of the free energy of the liquid and the free energy of the solid with these parameters phi and 1 minus phi. So if you're in the liquid, the order parameter is 0, you get the free energy of the liquid. If you're in the solid and the order parameter is 1, this goes away and you get the free energy of the solid. Same thing for the diffusion coefficient. When you're in the liquid, you get the diffusion coefficient of the liquid. When you're in the solid, you get the diffusion coefficient of the solid. This seems like a very natural thing to do. And notice what it's saying. It's saying that in the interface here, the free energy of the bulk material in the interface is some sort of linear combination between the solid and the liquid. And you can see that you're already beginning to get away from what really is going on here, right? You're kind of saying that, well, this is a computational method now, right? It doesn't really have much to do with the physics of what goes on at real interfaces, because I'm just taking a linear combination of the free energies, the bulk phases, to describe what goes on at the interface, right? So it's kind of a computational method now, and not what goes on in reality. The diffusion coefficient is the same way, right? So it's saying that the diffusion coefficient in the interface is some intermediate value between the liquid and the solid, which is probably reasonable, but it's saying a very specific kind of variation through the interface. And so these kind of assumptions turn out to have very big effects on what's going on at the interface, and I'll show you that in a second. So using this method, Jim Warren and Bill Bettinger did one of the first phase field calculations of alloy solidification in a dendrite. Looks like this. And so this is liquid, that's solid, obviously. What you're looking at here is the composition is a function of position. Low composition, high composition, blue is high. You can see that the solute is rejected at the interface because the solubility inside the dendrite is less than outside. You get non-uniform compositions in the dendrite as a function of position, kind of is exactly. If you look at any microstructure of a dendritic solidification process, you'd see precisely this. You'd see these stripes that go down the middle. It's called coring. You see all of this stuff that is segregated between these little secondary arms, exactly as you see. So it looks really good. And this is this paper. If you looked at ActaMed, it has over 500 citations.
What?
500.
Is
Okay.
that perfect four-fold symmetry?
Yeah. Okay. Okay. So now think about the pipe, right? This calculation is not quantitatively correct. It looks like a dendrite, kind of smells like a dendrite, but it is not a dendrite. And in fact, Bill Bettinger and Jim Warren would admit this. It is not quantitatively correct. So the amount of solute segregation that you get here is not correct. The amount of solute segregation you get in here is not correct, but it looks a lot like a dendrite. And so this is the challenge with phase field methods. And the big problem, and this is a very subtle thing, the big problem that they were unaware of when they used this kind of a model is that this reasonable assumption on how you interpolate from solid to liquid as you go through the interface gives you spurious terms in the diffusion equation. And actually, how you interpolate interfaces when you go from one to another in a phase field model is still an open question. But the takeaway message that I want you to be aware of is that whenever you see a phase field equation, a model, so this could be ferroelectric thin films, this could be magnetic materials. If you have structures that vary across the interface and you're interpolating across the interface, you will get physics at the interfaces that depend upon these interpolation functions that sometimes can be a problem. And in this particular problem, what happens is if you take those equations that I just showed you and you did these asymptotic expansions in this delta parameter delta where L divided by R is much, much less than 1, this is the equation that you want, that the velocity times the material rejected goes like the concentration gradients. And what you get instead is this equation. And this equation says that you have, instead of the jump in the concentration, you have a parameter times the thickness of the interface times h. And so what is that? It's actually a very simple physical explanation. So if you take a sphere, think about the interfacial area of a sphere here and a sphere here, right? So as the sphere grows, the interfacial area increases, right? If you have a very thick interface and lots of material associated with the interface, as it grows, you have to feed the material in the interface. And this sucks material out of what was supposed to go into the bulk. And so you get a term that's related to the thickness times the mean curvature. Over here, on the diffusion side, instead of getting bulk diffusion, this interface is so thick, you get surface diffusion. They are exactly correct that if you let the thickness of the interface, L, go to 0, these terms disappear. So if you use physically realistic interface sizes, these terms don't appear. But there's no way that you can use physical realistic interface sizes, so you get these spurious terms. And so to get rid of these terms, you have to do something very, very clever and very, very non-intuitive and reasonably complicated. And it goes back to some work of these folks here to get rid of these equations, to get rid of these problems. David brought up the fourfold anisotropy, and that turns out not to be a problem with these equations, but it turns out to be a problem with what happened in the early stages of phase field models. You notice the orientation of this dendrite is not along the XY directions of the grid. Okay, so the very first phase field models that people did, and there's a company that's I'm not on tape, am I? No. Okay. There's a company that markets a phase field code that you can buy, and when they first came out with this code, they had these beautiful dendrites, and you got beautiful dendrites when they grow along the grid, the XY coordinates of the grid. Because what was happening here is that the anisotropy of the grid would introduce enough anisotropy in the interfacial energy that you get beautiful dendrites going along these directions. And as soon as they refined the grid, the secondary dendrite arms disappeared, and you got blobs. Okay, and so Jim and Bill were very much aware of that, which is why it's canted at a strange angle with respect to the computational box. So they don't have that problem. But they have this far more subtle problem that basically, because they didn't do the matched asymptotic expansions, they didn't know that these terms existed in their calculations. And so the idea here, and I think I'll conclude, I'll stop with this slide, is that this thickness, which allows you to do all this marvelous stuff, in other words, topological transitions, very complicated morphologies, you can follow very, very easily, comes with it this penalty of extra terms in the diffusion equation and other situations that you have to watch out for when you're actually doing the calculations. And this is a generic effect. They're always going to be there. So, thanks very much. I'd be happy to answer some more questions if you have them.
Thank you, Peter, for a fantastic talk. Any questions?
Comments? Yes.
At the beginning of the talk, it seemed like everything seems like Lagrangian calculus, actually.
Right.
So why is it so hard to find what is the route that the composition or the order parameter is taking between two phases?
So why is it so hard?
Yeah, because it seems like a normal problem just in Lagrangian calculus.
Yeah. So the major problem is, I can kind of go all the way. Let me just. The problem is that the equations are highly nonlinear. Even in the Euler-Lagrange equations are nonlinear. So the key is to find solutions of the Euler-Lagrange equations. Where's the Cahn-Hilliard equation? Yeah, here. So if you just look at this equation, d phi dt equals like m the fourth derivative of phi. This is just a standard biharmonic, linear, constant coefficient. You do it in and after. That's no problems. The problem is this term. It's a derivative of this complicated polynomial function, and so it's nonlinear. And the nonlinearity sits inside gets operated on by del squared phi. And so it's that nonlinearity that makes them hard to solve. You can do it in one dimension, as I showed you, to get the interface. I think it was this one here. So in one dimension, this is what the polynomial looks like, the derivative in the simplest case, and you can get a solution. But in general, you can't solve the equation. So you can write what you're pointing out is a good one. There's a very strong connection between. Let me go back to the free energy. Yeah, there's a very strong connection between this and the evolution equations. And what that means is that that all of these equations decrease the energy of the system. And so you have this general energy framework that allows you to write things. So If you were doing magnetics, you could add magnetic energy. If you were doing electrostatics, you can add electrostatic energy. If you're doing elasticity, you just add more energy functions here. So it's very easy to generalize this, but that's the reason why it's so hard. It's just nonlinear. And in the solidification case, they're two coupled nonlinear PDEs, and so you just can't do much analytically with it. Yeah.
Is there some way? Oh, sorry.
Sorry, student first. Yes.
When you talk about mixtures, should you or can you discuss some kind of topic term for mixing?
This is a very, very good question. Yes, because yeah. So if I look at this thing, where is it? Oh, well, the free energy function is. I was just using phi squared 1 minus phi squared, right? Right. And in general, you would have these logarithmic terms. And in fact, if you're doing a real phase field model, you do put in those logarithmic terms. The problem with the logarithmic terms is that it makes the numerics much, much harder. And the reason why it makes numerics much, much harder is that, for example, if you have log x, so if you have a free energy function that looks like phi, like that, right? If you have this is plus some other terms in phi. Think about what happens when phi goes to 0. That diverges, right? This doesn't diverge, but the chemical potential, the variational derivative of this, the first derivative of f with respect to phi, goes like 1 over phi. And so you have terms that go like 1 over phi, and if you look at the free energy function, and this is why when you draw a free energy function, it actually, the slope here is infinity, and it comes down and does something like this. This slope of infinity, 1 over infinity, infinity, as phi goes to 0, makes implicit numerical methods of these equations extraordinarily difficult, and it's an unsolved problem. And so people will say all the time, you just write these nonlinear PDEs, especially if you go to a continuum mechanics group. They're very familiar with implicit methods, which basically make it easy to do time stepping. And say, well, just take these phase field equations and take my favorite finite element code, write an implicit solver, and as soon as you put in this thing, it doesn't work. And it's an unsolved problem at this point too. So realistic free energy functions, absolutely. In fact, if you want to connect with thermodynamic databases, you have to deal with these problems. And you just hope that any of the concentrations in the system are not too close to 0. And then you're probably okay. Yeah. David.
I'm just wondering, is there a way to rationalize or understand what we do, which is at the atomistic scale, with what the phase field, what you do? For instance, with a simple problem of coalescence of two precipitates.
Yeah.
So what we find is the compositions of the precipitates are changing with time.
Yeah.
And then from the LKMC, we find that the degree of order within the precipitate, the Braggs-Williams order parameters, changing with time, and that we think that the physical mechanism is that the vacancy is spending most of its time in the precipitates because of the interactions, the atomic interactions are going out to fourth nearest neighbors, and it's controlled by vacancy Solute term.
Yeah.
Whereas you're worried about this problem of stability of the system in between those 2 points.
Yeah. No, I think.
Which is quite different. I mean,
no, that's right. That's right.
When I look at that, I would say, okay, that's the activation energy barrier for exchange of a vacancy with an atom.
Yeah. One of the really interesting ideas is that during coalescence, what you do is you have two particles. For those of you who don't know what David's talking about, you take 2 particles, you bring them close together, and you think about what's happening. You have this diffuse interface over here. You have this diffuse interface over here. One particle, another particle. You have a diffuse interface. It does this, and you start bringing them close together. And they begin to come together, and this point here eventually disappears and the 2 particles coalesce. So this is the order parameter as a function of x. And so this is the coalescence region as you bring these 2 particles close together. And so what you're doing in here, when the particles coalesce, you're sampling the free energy in this region between 1 and 0. And so you're in this region here. And so as these particles coalesce, what you're doing is you're sampling the free energy in this unstable region. And so in principle, if you model your coalescence with these equations, you could actually pick out the right W's and epsilons to describe the coalescence process within a phase field model. So you could do it.
Maybe that's, the way we first described it, why you're getting this is we said, we know the interfaces are diffuse experimentally, so we said they're overlapping, these concentration profiles, so the free energy locally of the system is high compared to the case when they would connect the two particles.
Yeah.
Maybe that is the connection.
Yeah, I think so. And so in principle, you could actually model it carefully. Yeah, Bruce.
It seems to me that big problem is this W, and it's an artificial term.
Right.
And it's many valued. I guess that's what the statistical mechanics people are saying. So.
So that's right. I mean, and I think the connection, therefore, is with these macroscopic variables that people measure. And so if I don't have these values, I'm kind of sunk. It's very difficult for me to say what that really looks like.
Or does it have any?
Yeah. The closest thing that people have done to actually getting some idea as to what that looks like are in polymer systems where you have these big long chains, very, very mean field-like structures. But it's a major problem from the standpoint of a first principles method, where I asked Oswaldo to go into his quantum mechanics and molecular dynamics to tell me what that is. That's a pretty challenging problem.
Could you see with the phase field modeling what this problem of the interfacial width associated with the precipitates is continuously decreasing as the precipitates get bigger? That's an experimental fact.
No, you can do. That's right. And the key is in that case is to put together a model that accurately reflects the interface width in a real system, and you can do that if you choose the parameters the right way. It's certainly possible. Yeah, absolutely. Other questions?
Okay, so then let's thank Peter again.